From the earliest times, humans have gazed up at the night sky with a sense of wonder and awe. The twinkling stars, the distant planets, the ethereal glow of the Milky Way. These celestial objects have captivated our imaginations for millennia. We have woven stories about them, created myths and legends, and sought to understand our place in the grand tapestry of the cosmos. As we've developed tools and technologies to study the universe more closely, our fascination has only deepened. Each new discovery, from the vastness of interstellar space to the intricate workings of distant galaxies, has unveiled more mysteries and ignited our curiosity further. The study of space is not merely an academic pursuit, it is a profound journey of self-discovery. By exploring the cosmos, we gain a deeper understanding of our own planet, our origins, and the fundamental laws that govern the universe we inhabit. In this exploration of mind-blowing space discoveries, we will embark on a journey through the cosmos, delving into some of the most remarkable findings that have reshaped our understanding of the universe and our place within it. Our universe is a place of astonishing scale, complexity, and beauty. Within its vast expanse lies celestial objects and phenomena that defy imagination, black holes that warp the fabric of space-time, galaxies that span hundreds of thousands of light-years, and the faint whispers of the Big Bang, the event that brought our universe into existence. The past century in particular has witnessed an unprecedented explosion of knowledge about the cosmos. Advances in telescope technology, space exploration missions, and theoretical physics have allowed us to probe deeper into the universe's mysteries than ever before. We've discovered planets orbiting distant stars, some of which may harbor conditions suitable for life. We've witnessed the cataclysmic deaths of stars, explosions that seed the universe with the elements necessary for life. And we've begun to unravel the secrets of dark matter and dark energy, enigmatic forces that shape the universe's evolution and hold the key to understanding its ultimate fate. For centuries, our understanding of the cosmos was based on observation from Earth and limited by the capabilities of our instruments. Ancient astronomers meticulously charted the movements of stars and planets, developing intricate models to explain their observations. While these early astronomers made remarkable strides, many of their ideas were based on speculation and philosophical reasoning. The invention of the telescope in the 17th century revolutionized astronomy, allowing us to see celestial objects in greater detail than ever before. However, it was the development of spaceflight in the 20th century that truly opened up the cosmos to exploration. Rockets and spacecraft allowed us to break free from the constraints of Earth's atmosphere and send probes, telescopes, and even humans into the depths of space. This ability to directly explore our celestial neighborhood has led to an explosion of knowledge, confirming some long-held theories while overturning others, and revealing a universe far stranger and more wondrous than we could have imagined. Our quest to understand the universe is driven by a combination of curiosity and the development of increasingly sophisticated tools. Telescopes, both on Earth and in space, allow us to observe distant objects across the electromagnetic spectrum, from radio waves to gamma rays. Spacecraft, equipped with an array of scientific instruments, have ventured to all the planets in our solar system and beyond, beaming back data that has revolutionized our understanding of planetary science. And rovers have explored the surface of Mars, searching for signs of past or present life and paving the way for future human missions. But our tools are not limited to physical instruments. Theoretical physicists develop complex mathematical models and simulations to explain the behavior of the universe on its grandest scales, from the Big Bang to the formation of galaxies. These theoretical frameworks, combined with observational data, allow us to test our understanding of the universe and make predictions about phenomena that we have yet to observe directly. Section 5. Expanding our cosmic horizons. Each new discovery in space expands our cosmic horizons, pushing the boundaries of our knowledge and challenging us to rethink our place in the universe. The realization that our Sun is just one of billions of stars in the Milky Way galaxy, and that our galaxy is itself one of billions of galaxies in the observable universe, has profoundly shifted our perspective. We now know that the universe is not a static, unchanging realm, but a dynamic and evolving entity. Galaxies collide and merge, stars are born and die, and black holes warp the fabric of space-time. The study of space is not just about understanding the objects and phenomena that exist in the universe. It's also about understanding the processes that drive its evolution and the fundamental laws that govern its behavior. By studying the cosmos, we gain insights into the nature of gravity, the behavior of matter and energy at extreme temperatures and densities, and the origins of the universe itself. Section 6, the quest for knowledge continues. Our exploration of the cosmos is far from over. As we continue to develop new technologies and refine our theoretical models, we can expect even more mind-blowing discoveries in the years and decades to come. The James Webb Space Telescope, launched in 2021, promises to revolutionize our understanding of the early universe, allowing us to peer back in time to observe the formation of the first stars and galaxies. New generations of ground-based telescopes will probe the universe in unprecedented detail, searching for signs of life beyond Earth and unraveling the mysteries of dark matter and dark energy. And ambitious space missions are being planned to explore the icy moons of Jupiter and Saturn, worlds that may harbor vast oceans of liquid water beneath their frozen surfaces and hold the potential for extraterrestrial life. The quest for knowledge is a journey without end, and the cosmos offers an endless frontier of discovery. As we continue to explore the universe around us, we can be certain that the most astonishing discoveries are yet to come. Section 1. A static universe challenged. For centuries, the prevailing view of the universe was one of immutability and permanence. The stars and galaxies, it was believed, were fixed in their positions, forming an unchanging cosmic tapestry. This view, rooted in philosophical and religious beliefs, was challenged in the early 20th century by a series of groundbreaking astronomical observations. One of the key figures in this revolution was the American astronomer Edwin Hubble, whose meticulous observations of distant galaxies would forever alter our understanding of the cosmos. Hubble's work, conducted at the Mount Wilson Observatory in California, focused on measuring the distances and velocities of galaxies far beyond our own Milky Way. At the time, the nature of these fuzzy, spiral-shaped objects known as nebulae was still a matter of debate. Some astronomers believed they were relatively small objects located within our own galaxy, while others argued that they were vast independent island universes scattered throughout space. Hubble's observations, made possible by the powerful Hooker telescope at Mount Wilson, provided compelling evidence in favor of the latter view. By measuring the distances to these nebulae, Hubble showed that they were far too distant to be part of the Milky Way, confirming their status as separate galaxies. Section 2, Hubble's observations, galaxies on the move. Hubble's discovery of the extragalactic nature of these nebulae was groundbreaking in itself, but it was his subsequent observations of their motions that would lead to one of the most profound discoveries in the history of astronomy. Hubble noticed something peculiar in the light coming from these distant galaxies. When he analyzed the spectra of their light, the rainbow-like patterns produced when light is split into its different wavelengths, he found that the spectral lines, which correspond to specific elements within the galaxies, were shifted from their expected positions. This phenomenon, known as redshift, had been observed before in the light from stars within our own galaxy, but Hubble's observations showed that the redshift of light from distant galaxies was far more pronounced. Moreover, there was a clear correlation between a galaxy's distance and the amount of its redshift. The farther away a galaxy was, the more its light was shifted towards the red end of the spectrum. This observation, known as Hubble's law, would have profound implications for our understanding of the universe's evolution. Section 3, redshift, the Doppler effect of light. To understand the significance of Hubble's observations, we need to delve into the physics behind redshift. Redshift is a manifestation of the Doppler effect, a phenomenon observed in all types of waves, including sound and light. The Doppler effect describes the change in frequency or wavelength of a wave as perceived by an observer relative to the source of the wave. When a source of waves is moving towards an observer, the waves are compressed, resulting in a higher frequency or shorter wavelength. Conversely, when a wave source is moving away from an observer, the waves are stretched out, resulting in a lower frequency or longer wavelength. This is why the siren of an approaching ambulance sounds higher pitched as it gets closer and lower pitched as it moves away. The same principle applies to light waves. When a light source is moving away from us, its light waves are stretched, causing its spectral lines to shift towards the red end of the spectrum, hence the term redshift. The amount of redshift is directly proportional to the speed at which the light source is receding from us. Section 4, the expanding universe, a paradigm shift. Hubble's observations of galactic redshifts, combined with his measurements of their distances, led him to a startling conclusion. The universe is expanding. The systematic redshift of light from distant galaxies indicated that they were all moving away from us and from each other. Furthermore, the relationship between redshift and distance implied that the farther away a galaxy was, the faster it was receding. This observation could not be explained if the universe was static and unchanging. Hubble's discovery of the expanding universe was a paradigm shift in cosmology, overturning centuries of belief in a static cosmos. It implied that the universe was not eternal and unchanging, but had a beginning, a point in time when everything was much closer together. This realization paved the way for the development of the Big Bang theory, which posits that the universe originated from an extremely hot, dense state and has been expanding and cooling ever since. Hubble's observations, initially met with skepticism, provided the first observational evidence for this revolutionary idea, forever changing our understanding of the cosmos and our place within it. Echoes of the Big Bang. The Big Bang theory describes a cosmos that began in an incredibly hot, dense state and has been expanding and cooling ever since. In the 1960s, a remarkable discovery provided compelling evidence for the Big Bang. Two scientists found a persistent hum interfering with their radio antenna. This interference was a faint echo from the universe's earliest moments. Known as the cosmic microwave background, or CMB, it is a faint afterglow of the Big Bang. The CMB provided the first direct evidence of the universe's hot, dense beginning. Serendipitous discovery, a persistent hum. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Telephone Laboratories in New Jersey, testing a new type of microwave antenna designed for satellite communication. As they calibrated their instrument, they noticed a persistent background noise, a faint hum that seemed to come from every direction in the sky. At first, they suspected the interference might be coming from nearby New York City or even from pigeon droppings on their antenna. They meticulously cleaned the antenna and tried various other solutions, but the mysterious noise persisted. Unbeknownst to Penzias and Wilson, just a short distance away at Princeton University, a team of physicists led by Robert Dicker was actively searching for evidence of the Big Bang's afterglow. Dicker's team had calculated that if the Big Bang theory was correct, there should be a faint background radiation permeating the universe, a remnant of the intense heat of the early cosmos. When Penzias and Wilson heard about Dicker's work, they realized that the annoying hum they had been trying to eliminate was precisely the signal that Dicker's team was seeking. The two teams published their findings jointly in 1965, with Penzias and Wilson describing their discovery of the background radiation and Dicker's team providing the cosmological interpretation. The cosmic afterglow, a window to the early universe. The cosmic microwave background radiation is often described as an afterglow of the Big Bang, because it originated from a time when the universe was much hotter and denser than it is today. In the first few 100,000 years after the Big Bang, the universe was a seething cauldron of elementary particles, photons, and a hot ionized plasma. As the universe expanded and cooled, a crucial transition occurred. The temperature dropped to a point where protons and electrons could combine to form neutral hydrogen atoms, a process known as recombination. This transition had a profound effect on the universe's transparency. Before recombination, the universe was opaque to light because photons were constantly scattering off the free electrons in the plasma. But after recombination, with the electrons bound up in hydrogen atoms, the universe became transparent, allowing photons to travel freely through space. The cosmic microwave background radiation we observe today consists of these ancient photons released from the cosmic plasma at the time of recombination. These photons have been traveling through the universe ever since, carrying with them a faint imprint of the conditions that existed in the early cosmos. Section 4. Temperature fluctuations, seeds of structure. Initial measurements of the cosmic microwave background radiation revealed it was incredibly uniform. However, the universe today is not perfectly smooth. It is filled with galaxies and clusters, indicating initial density fluctuations. Tiny temperature fluctuations in the CMB correspond to regions of higher or lower density. These regions eventually collapsed to form galaxies, stars, and planets. The search for other worlds. For millennia, humans have gazed upon the stars and wondered if other worlds like our own Earth might exist. This age-old question has become a vibrant field of scientific inquiry, fueled by technological advancements. The search for exoplanets has captured the imagination of scientists and the public alike. Discoveries have expanded our understanding of planetary systems in the universe. Section 2. The Kepler mission. A planet-hunting telescope launched in 2009, Kepler searched for Earth-sized planets. It monitored over 150,000 stars. Detecting minute dips in brightness, it found planets. This method is known as the transit method. Kepler's precision was like seeing a flea on a headlight from miles away. Kepler identified planets orbiting distant stars. Section 3. Transiting planets, detecting distant worlds. The transit method, while incredibly powerful, has its limitations. Not every planet will transit its star from our perspective on Earth. For a transit to occur, the planet's orbital plane must be aligned edge-on to our line of sight. Despite this limitation, the transit method has proven to be remarkably successful. Section 4. Kepler's bounty, a diversity of planetary systems. Kepler's tireless observations spanning nearly a decade revolutionized our understanding of planetary systems beyond our own. The mission revealed that planets are incredibly common in the Milky Way galaxy, with many stars hosting multiple planets. Kepler's discoveries also shattered our preconceived notions about the diversity of planetary systems. The mission uncovered a bewildering array of planets, from hot Jupiters, gas giants orbiting scorchingly close to their stars, to super-Earths, rocky planets larger than Earth but smaller than Neptune, to mini-Neptunes, planets with thick atmospheres and possibly liquid water oceans beneath. Kepler's data revealed that our own solar system, once thought to be typical, is actually quite unusual in its architecture. The mission found that most planetary systems are tightly packed, with planets orbiting much closer to their stars than the planets in our solar system. This discovery has led astronomers to rethink theories of planet formation and migration, suggesting that planets may form in one location and then migrate inward or outward over time due to gravitational interactions with their stars or other planets. Kepler's legacy extends far beyond its impressive catalogue of exoplanet discoveries. The mission's data continues to be analyzed, yielding new insights into the demographics of planetary systems, the properties of exoplanet atmospheres, and the potential habitability of worlds beyond our own. Section 1. The Enigma of Black Holes. Black holes stand as some of the most captivating and enigmatic objects in the cosmos, celestial entities so extreme that they challenge our very understanding of space, time, and gravity. These cosmic monsters, born from the death throes of massive stars, possess gravitational pull so intense that nothing, not even light, can escape their grasp once it crosses a certain boundary known as the event horizon. The concept of black holes emerged from Albert Einstein's groundbreaking theory of general relativity, which revolutionized our understanding of gravity. Einstein's theory describes gravity not as a force acting at a distance, but as a curvature of space-time, caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline. The ball's weight causes the trampoline's surface to sag, creating a curvature. Similarly, massive objects like stars and planets warp the fabric of space-time around them. The more massive the object, the greater the curvature it induces. Black holes represent the ultimate manifestation of this curvature. When a sufficiently massive star exhausts its nuclear fuel and can no longer support itself against its own gravity, it undergoes a catastrophic collapse, imploding in on itself and creating a region of space-time so profoundly warped that it effectively becomes cut off from the rest of the universe. This region is what we call a black hole. Gravity's ultimate triumph, the event horizon. At the heart of a black hole lies a point of infinite density known as the singularity, where the laws of physics as we know them break down. Surrounding the singularity is a boundary called the event horizon, a region of no return for anything that ventures too close. The event horizon is not a physical barrier, but rather a point of no return for light and matter. Inside the event horizon, the pull of gravity is so strong that even light, the fastest thing in the universe, cannot escape. Imagine shining a flashlight towards a black hole from just outside the event horizon. The light beam, while initially traveling at its characteristic speed, would be inexorably drawn towards the black hole's center, its path bent more and more sharply as it approached the event horizon. Upon reaching the event horizon, the light beam would be completely trapped, unable to escape the black hole's gravitational pull. From an outside observer's perspective, it would appear as if the light beam had simply vanished. Its energy redshifted to longer and longer wavelengths until it became undetectable. Seeing the unseeable, the Event Horizon Telescope, black holes, by their very nature, pose a significant challenge for observation. Since no light can escape from within the event horizon, black holes themselves are inherently invisible against the backdrop of space. However, astronomers have developed ingenious methods to indirectly infer the presence of black holes by observing their effects on their surroundings. One such method involves studying the motion of stars and gas clouds orbiting around a suspected black hole. By carefully tracking the trajectories of these objects, astronomers can calculate the mass of the unseen object at the center, providing strong evidence for the existence of a black hole. Another method involves observing the radiation emitted by matter as it spirals inward towards a black hole, heated to extreme temperatures by the intense gravitational forces. However, a groundbreaking international collaboration known as the Event Horizon Telescope, or EHT, set out to achieve what was once thought impossible, to capture a direct image of a black hole's event horizon. A historic image, M87** shadow. The Event Horizon Telescope is not a single telescope, but rather a global network of radio telescopes, scattered across continents and linked together using a technique called Very Long Baseline Interferometry, or VLBI. By combining the signals from these widely spaced telescopes, the EHT effectively creates a virtual telescope with an aperture the size of Earth, giving it the resolving power needed to observe the incredibly small region of space surrounding a black hole's event horizon. In April 2019, the EHT collaboration made history by unveiling the first ever image of a black hole's event horizon. The image, a stunning achievement in observational astronomy, showed a bright ring of light surrounding a dark central region, the shadow of the supermassive black hole known as M87** at the heart of the galaxy Messier 87, located some 55 million light-years from Earth. The bright ring represents the light emitted by hot gas swirling around the black hole, its path bent and distorted by the intense gravity. The dark central region, the shadow of the black hole, corresponds to the region where light is unable to escape, providing direct visual evidence for the existence of an event horizon, a point of no return for light and matter. Ripples in space-time. A prediction from Einstein. Albert Einstein revolutionized our understanding of gravity with his general theory of relativity, published in 1915. Gravity is a curvature of space-time caused by mass and energy. Einstein predicted gravitational waves, ripples in space-time from accelerating massive objects. Like a boat creating ripples, accelerating objects generate gravitational waves. A cosmic symphony, the nature of gravitational waves. Gravitational waves are not like sound waves that travel through the air or light waves that travel through space. Instead, they are disturbances in the very fabric of space-time itself, stretching and squeezing the distance between objects as they pass by. Imagine two people holding opposite ends of a trampoline. If one person suddenly jumps up and down, the trampoline's surface will vibrate, creating waves that travel towards the other person. Similarly, when massive objects in space accelerate, they generate gravitational waves that propagate outward, stretching and compressing the fabric of space-time as they go. These waves, however, are incredibly weak, far fainter than any other signals we detect from the cosmos. To put their strength into perspective, a gravitational wave passing through Earth would only cause a minuscule change in the distance between two objects, a change far smaller than the width of an atom. Despite their extraordinary weakness, gravitational waves carry a wealth of information about the objects and events that created them. By studying the properties of these waves, their frequency, amplitude, and polarization, astronomers can learn about the masses, spins, and orbital characteristics of the objects involved, providing unique insights into some of the most energetic and cataclysmic events in the universe. The challenge of detection listening for the faintest tremors. Detecting gravitational waves proved to be an immense technological challenge, one that would elude scientists for decades after Einstein first predicted their existence. The extreme faintness of these waves, combined with the subtle nature of their effects on space-time, demanded extraordinary sensitivity and ingenuity in experimental design. Early attempts to detect gravitational waves relied on resonant bar detectors, massive metal cylinders designed to vibrate at a specific frequency when struck by a passing gravitational wave. These detectors, however, were limited in their sensitivity and could only detect waves from extremely rare and energetic events, such as the collision of two neutron stars in our own galaxy. A breakthrough came in the 1970s with the development of laser interferometry, a technique that could, in principle, detect the minuscule changes in distance caused by passing gravitational waves with far greater sensitivity than resonant bar detectors. Laser interferometers work by splitting a laser beam into two paths and sending them down perpendicular arms, where they are reflected back by mirrors and recombined. If a gravitational wave passes through the interferometer, it will stretch and squeeze the arms by an infinitesimally small amount, causing a shift in the interference pattern of the recombined laser beams. Building a laser interferometer sensitive enough to detect gravitational waves required pushing the limits of precision engineering and overcoming formidable technological hurdles. This ambitious goal was taken up by the Laser Interferometer Gravitational Wave Observatory, or LIGO, a large-scale scientific collaboration involving hundreds of scientists and engineers from around the world. The LIGO project consists of two identical interferometers, one located in Hanford, Washington, and the other in Livingston, Louisiana, separated by nearly 2,000 miles. Each interferometer has two arms, each 2.5 miles long, housed in ultra-high vacuum tubes to minimize noise from air molecules and seismic vibrations. The mirrors at the ends of the arms, suspended from sophisticated seismic isolation systems, are polished to an astonishing degree of smoothness, with imperfections less than 1,000th the width of a human hair. These mirrors act as test masses, their relative positions monitored with exquisite precision by the laser beams reflecting back and forth between them. Even with these extraordinary measures, isolating the faint whispers of gravitational waves from the cacophony of background noise, from seismic vibrations to thermal fluctuations in the mirrors themselves, remained a daunting challenge, requiring sophisticated data analysis techniques and a deep understanding of the instrument's behavior. On September 14, 2015, at 9:50 a.m. UTC, a faint chirp appeared in the data from both LIGO detectors. It matched the predictions for gravitational waves from two black holes colliding over 1 billion light-years away. The signal carried information about the event, revealing the masses of the black holes. They orbited at high speeds before merging, releasing energy equivalent to 3 suns. This detection marked a watershed moment in astronomy, confirming Einstein's theory. The detection of gravitational waves by LIGO opened a new window on the universe, providing astronomers with a fundamentally new way to observe the cosmos and study some of its most violent and enigmatic phenomena. Unlike light, which can be absorbed, scattered, or blocked by matter, gravitational waves travel unimpeded through the universe, carrying pristine information about the events that created them. Gravitational wave astronomy is often likened to listening to the universe as opposed to seeing it with telescopes. Just as sound waves can reveal information about a distant event, the roar of a lion, the crash of thunder, so too can gravitational waves provide unique insights into the dynamics of objects and events that are invisible to traditional telescopes. The detection of gravitational waves from merging black holes, once thought to be impossible to observe directly, has provided compelling evidence for their existence and given astronomers new tools to study their properties, such as their masses, spins, and orbital characteristics. Furthermore, gravitational wave detectors like LIGO are sensitive to a wide range of cosmic events, including supernova explosions, the collisions of neutron stars, and even the faint whispers of the Big Bang itself, offering the tantalizing possibility of probing the universe's earliest moments. Section 7. Cosmic collisions. Unveiling the secrets of black holes and neutron stars. Since the first detection of gravitational waves in 2015, LIGO and its European counterpart Virgo have detected dozens of signals from merging black holes, confirming the existence of these once hypothetical objects and providing a wealth of data about their properties and behavior. These detections have revealed a surprising diversity in black hole masses, with some mergers involving black holes significantly more massive than those previously observed using traditional astronomical techniques. This finding has challenged our understanding of how these massive objects form and evolve, suggesting that there may be multiple pathways to their creation. In 2017, LIGO and Virgo made another groundbreaking discovery, detecting gravitational waves from the merger of two neutron stars, the collapsed cores of massive stars that exploded as supernovae. This detection was particularly exciting because it was accompanied by a burst of electromagnetic radiation observed by telescopes across the electromagnetic spectrum from gamma rays to radio waves. This multi-messenger observation, the first of its kind, allowed astronomers to study the event in unprecedented detail, providing insights into the physics of neutron star mergers, the origin of heavy elements like gold and platinum, and the expansion rate of the universe. Section 8. The future of gravitational wave astronomy. Listening to the universe's deepest secrets. Gravitational wave astronomy is in its infancy but holds immense promise. Future detectors like the Einstein telescope and LISA will be more sensitive than LIGO and Virgo. Detecting signals from distant and faint sources, they will probe the universe's gravitational wave landscape, revealing the hidden workings of gravity and the origins of the universe. Section 1. The mystery of missing mass. Our exploration of the cosmos has revealed a universe far grander and more mysterious than we could have imagined. Amidst the swirling galaxies, blazing stars, and enigmatic black holes lies a profound puzzle, a cosmic conundrum that has captivated astronomers and physicists for decades, the mystery of missing mass. The story begins with the study of galaxies, those vast islands of stars, gas, and dust scattered throughout the cosmos. By observing the rotation of galaxies, astronomers can measure their masses. However, when they compared these measurements to the amount of visible matter in galaxies, stars, gas, and dust, they encountered a startling discrepancy. The galaxies were spinning far too fast for the amount of visible matter they contained. The stars in these galaxies should have been flung outward, like passengers on a carousel spinning out of control, yet they remained gravitationally bound, held together by some invisible hand. This discrepancy, known as the missing mass problem, hinted at the existence of a mysterious substance, unseen and undetected by our telescopes, yet exerting a powerful gravitational influence on the visible universe. This elusive substance, dubbed dark matter, would become one of the most profound mysteries in modern cosmology. Section 2. Dark matter, the invisible hand. Dark matter, as its name implies, does not emit, absorb, or reflect light, making it invisible to our telescopes, which rely on detecting electromagnetic radiation. Its presence can only be inferred indirectly through its gravitational effects on the visible matter around it. Imagine a bowling ball hidden beneath a blanket on a trampoline. While you can't see the bowling ball, you can infer its presence by observing how it distorts the blanket's surface, creating a dip that attracts other objects placed nearby. Similarly, dark matter's gravitational influence reveals itself in various ways, from the rotation of galaxies to the bending of light from distant objects. Despite its elusiveness, dark matter is thought to make up the vast majority of the universe's matter content, outweighing visible matter by a factor of roughly 6 to 1. Astronomers and physicists have proposed various candidates for the composition of dark matter, ranging from exotic subatomic particles to faint, low-mass stars. However, despite decades of intensive research, the true nature of dark matter remains one of the most tantalizing mysteries in modern science. Section 3. Mapping the invisible evidence for dark matter. The evidence for dark matter's existence extends far beyond the rotation of individual galaxies. Astronomers have observed its gravitational signature on a vast range of cosmic scales, from the clustering of galaxies to the bending of light from distant objects, a phenomenon known as gravitational lensing. Gravitational lensing occurs when the gravity of a massive object, such as a galaxy cluster, distorts the fabric of space-time, causing light from more distant objects to bend around it, creating multiple distorted images of the background object. By studying the shape and brightness of these lensed images, astronomers can infer the mass of the intervening object, including both its visible and dark matter content. Observations of gravitational lensing have provided some of the most compelling evidence for dark matter's existence, revealing the presence of vast halos of dark matter surrounding galaxies and clusters of galaxies, extending far beyond their visible boundaries. Furthermore, the cosmic microwave background radiation, the faint afterglow of the Big Bang, carries within its temperature fluctuations a subtle imprint of the universe's early composition, including the relative amounts of dark matter, normal matter, and dark energy. These observations have provided further support for the existence of dark matter and have allowed cosmologists to refine their models of the universe's evolution. Section 4. The Accelerating Universe, a Cosmic Enigma. As if the mystery of dark matter wasn't enough to keep cosmologists busy, another profound discovery in the late 1990s shook the foundations of our understanding of the universe. The realization that the expansion of the universe, first observed by Edwin Hubble in the 1920s, was not slowing down as expected, but was instead accelerating. This startling discovery emerged from observations of distant supernovae, exploding stars that serve as standard candles for measuring cosmic distances. By studying the brightness and redshift of these supernovae, astronomers could trace the universe's expansion history, determining how its expansion rate has changed over billions of years. To their astonishment, the astronomers found that the most distant supernovae, those that exploded when the universe was much younger, were fainter than expected, implying that they were farther away than predicted by a universe expanding at a constant or decelerating rate. This unexpected faintness indicated that something was causing the universe's expansion to speed up, a finding that challenged the prevailing view that the universe's expansion should be slowing down over time due to the gravitational pull of matter. This mysterious force, responsible for the universe's accelerated expansion, was dubbed dark energy. Section 5. Dark energy, the force behind the expansion. Dark energy, unlike dark matter, is not thought to clump together under the influence of gravity. Instead, it is believed to be a property of space itself, a kind of cosmic anti-gravity that pushes everything apart, causing the universe's expansion to accelerate. One way to think about dark energy is to imagine blowing up a balloon. As you blow air into the balloon, the rubber stretches, causing the balloon to expand. Similarly, as the universe expands, more space is created, and this creation of space is thought to be accompanied by the emergence of more dark energy, further accelerating the expansion. The nature of dark energy remains one of the most profound mysteries in modern cosmology. Some physicists speculate that it might be related to the energy inherent in the vacuum of space itself, a concept known as the cosmological constant, first proposed by Albert Einstein in the context of his general theory of relativity. Others have proposed alternative theories involving new fundamental forces or modifications to our understanding of gravity on cosmic scales. Unraveling the nature of dark energy is a major focus of ongoing research, with profound implications for our understanding of the universe's fate. And Section 6. Probing the darkness, the search for answers. The quest to understand dark matter and dark energy has become one of the most compelling frontiers in modern cosmology and particle physics. Astronomers and physicists are pursuing a multi-pronged approach, combining observations from ground-based and space-based telescopes with theoretical modeling and particle physics experiments to shed light on these enigmatic entities. On the observational front, astronomers are using a variety of techniques to map the distribution and properties of dark matter and dark energy, including gravitational lensing, galaxy surveys, and studies of the cosmic microwave background radiation. These observations provide crucial data for constraining cosmological models and testing theories about the nature of dark matter and dark energy. Particle physicists are also playing a crucial role in the search for dark matter, conducting experiments at particle accelerators like the Large Hadron Collider to search for new subatomic particles that might interact with normal matter only through gravity, making them ideal dark matter candidates. Theoretical physicists, meanwhile, are developing new theories and refining existing ones to explain the observed properties of dark matter and dark energy, exploring a wide range of possibilities, from modifications to our understanding of gravity to the existence of extraspatial dimensions. Section 7, A Universe of Unknowns, Dark Matter and Dark Energy's Profound Implications. The realization that the vast majority of the universe's mass and energy content is in the form of dark matter and dark energy, substances about which we know very little, has profoundly altered our understanding of the cosmos and our place within it. Dark matter's gravitational influence is thought to have played a crucial role in the formation of galaxies and the large-scale structure of the universe. Its presence provided the gravitational scaffolding upon which normal matter could clump together, forming the stars, galaxies, and planets we observe today. Dark energy, on the other hand, is driving the universe's accelerated expansion, counteracting the pull of gravity and determining the ultimate fate of the cosmos. Whether the universe's expansion will continue to accelerate indefinitely, leading to a big rip scenario, or whether dark energy's influence will eventually wane, allowing gravity to regain control, remains an open question. The quest to understand dark matter and dark energy is not merely an academic pursuit. It strikes at the heart of our understanding of the universe's origins, its evolution, and its ultimate destiny. Section 8, the quest continues, unveiling the dark side of the cosmos. The story of dark matter and dark energy is still being written. Each new observation, each theoretical breakthrough, each particle physics experiment brings us closer to unraveling these cosmic enigmas. The quest to understand the dark side of the cosmos is a testament to the power of human curiosity and our relentless pursuit of knowledge. As we delve deeper into the universe's hidden realms, we can be certain that even more surprises await us, challenging our preconceived notions and expanding our understanding of the cosmos and our place within it. The universe is a vast and mysterious place, and the more we learn about it, the more we realize how much more there is to discover. The mysteries of dark matter and dark energy serve as powerful reminders that we live in a universe full of wonder, and the quest to understand it will continue to inspire generations to come. The future of cosmology is bright, filled with the promise of new discoveries that will illuminate the universe's darkest corners and reshape our understanding of the cosmos we call home. Section 1. Stellar evolution, the life and death of stars. Stars, those brilliant beacons scattered across the cosmos, are not eternal. They are born, they live, and they die. Their life cycles governed by a delicate balance between the inward pull of gravity and the outward push of nuclear fusion, the process that powers their radiant energy. The fate of a star, its ultimate demise, is largely determined by its mass, a key factor in shaping its evolutionary path. Stars like our Sun, classified as main sequence stars, spend the majority of their lives fusing hydrogen into helium in their cores, releasing a tremendous amount of energy in the process. This nuclear fusion acts as a stellar thermostat, keeping the star stable for billions of years. However, as a star ages, it gradually exhausts its hydrogen fuel, upsetting the delicate balance between gravity and nuclear fusion. The core begins to contract, heating up and triggering a series of nuclear reactions that produce heavier elements such as carbon, oxygen, and neon. The star's outer layers, meanwhile, expand and cool, transforming it into a red giant, a bloated star hundreds of times larger than its original size. The fate of a red giant, however, depends on its mass. Stars like our Sun will eventually shed their outer layers, forming planetary nebulae, leaving behind their dense, hot cores as white dwarfs. Section 2. Neutron stars, cosmic cinders. For stars significantly more massive than our Sun, the evolutionary path takes a more dramatic turn. As these massive stars exhaust their nuclear fuel, their cores collapse under their own immense gravity, triggering a cataclysmic explosion known as a supernova, one of the most energetic events in the universe. During a supernova, the star's core is compressed to an extraordinarily dense state, squeezing protons and electrons together to form neutrons, subatomic particles with no electrical charge. This compressed core, if its mass is less than about 3 times the mass of the Sun, becomes a neutron star, a celestial object of almost unimaginable density. Imagine squeezing the entire mass of our Sun, a sphere, with a diameter of 1.4 million kilometers, into a ball just a few kilometers across. That's the extraordinary density of a neutron star, a teaspoonful of which would weigh billions of tons on Earth. Neutron stars are not merely incredibly dense, they also rotate rapidly, often spinning hundreds of times per second, and possess incredibly strong magnetic fields, trillions of times stronger than Earth's magnetic field. These extreme properties make neutron stars some of the most fascinating and exotic objects in the cosmos. In 1967, a young graduate student named Jocelyn Bell Burnell, working at the Mullard Radio Astronomy Observatory in Cambridge, England, stumbled upon a peculiar signal while analyzing data from a new radio telescope. The signal, a series of regular pulses of radio waves, arrived like clockwork, repeating every 1.33 seconds. Initially, Belle Burnell and her supervisor, Anthony Hewish, considered the possibility that the signal might be artificial, perhaps from an extraterrestrial civilization. However, after ruling out other potential sources, they realized that they had discovered a new type of celestial object, one that would later be known as a pulsar. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As a pulsar spins, its beams of radiation sweep across space like the beams from a lighthouse. If Earth happens to lie in the path of one of these beams, we detect a pulse of radiation each time the beam sweeps past us. Hence the name pulsar. The discovery of pulsars caused a sensation in the astronomical community, providing the first observational evidence for the existence of neutron stars, which had been predicted theoretically decades earlier. Pulsars have since become invaluable tools for studying a wide range of astrophysical phenomena, from the properties of matter under extreme conditions to the structure of our galaxy. The regular pulses of radiation emitted by pulsars make them incredibly precise cosmic clocks, some of which rival the accuracy of atomic clocks on Earth. This remarkable precision has made pulsars invaluable tools for testing Einstein's general theory of relativity, which describes gravity as a curvature of space-time. According to general relativity, massive objects like neutron stars should distort the fabric of space-time around them, causing a delay in the arrival times of signals passing through this curved region. By carefully timing the arrival of pulses from pulsars located behind massive objects like our Sun, astronomers can measure this time delay, known as the Shapiro delay, and confirm the predictions of general relativity. Furthermore, some pulsars are found in binary systems orbiting around a companion star. These binary pulsars provide an even more stringent test of general relativity, allowing astronomers to study the effects of strong gravity on the orbital motion of these extreme systems. Observations of binary pulsars have confirmed the existence of gravitational waves, ripples in the fabric of space-time predicted by Einstein's theory, and have provided precise measurements of their effects on the orbital decay of these systems, further solidifying the foundations of general relativity as our best description of gravity. While all neutron stars possess incredibly strong magnetic fields, a rare and enigmatic subclass known as magnetars takes this magnetism to an extreme. Magnetars are neutron stars with magnetic fields thousands of times stronger than those of typical neutron stars, reaching strengths of up to a quadrillion Gauss, billions of times stronger than the strongest magnetic fields ever produced in a laboratory on Earth. The origin of these extreme magnetic fields is still debated, but they are thought to be related to the rapid rotation and complex internal dynamics of these newly formed neutron stars. These intense magnetic fields can have dramatic effects on the star's surface and its surrounding environment. Magnetars are known to erupt with powerful bursts of X-rays and gamma rays, thought to be caused by star quakes, sudden shifts in the star's crust triggered by the immense stresses exerted by its powerful magnetic field. These bursts can be so bright that they can briefly outshine all the other X-ray sources in our galaxy combined. The study of magnetars provides a unique window into the physics of matter under extreme magnetic conditions, a regime far beyond anything we can replicate in laboratories on Earth. These extreme objects continue to challenge our understanding of neutron star physics and the fundamental limits of magnetic field strengths in the universe. Section 6. Neutron Star Interiors, a Cosmic Laboratory. Neutron stars serve as cosmic laboratories for studying matter under extreme conditions. Their interiors, compressed to densities exceeding atomic nuclei, push the limits of physics. At the surface, atoms are crushed, forming a sea of neutrons. This neutron-rich matter, known as nuclear pasta, has a complex structure. Theoretical models predict exotic particles like hyperons and strange quarks. Combining observations with models, scientists explore this fascinating world. Section 7. Neutron Star Mergers, Cosmic Fireworks. Just as black holes can collide and merge, releasing tremendous amounts of energy in the form of gravitational waves, so too can neutron stars. These neutron-star mergers are some of the most energetic events in the universe, briefly outshining entire galaxies and forging heavy elements such as gold and platinum in their fiery aftermath. When two neutron stars collide, they spiral inward, their orbital energy dissipated through the emission of gravitational waves. As the stars draw closer, they distort each other's shapes, stretching and squeezing them like cosmic Play-Doh, further intensifying the gravitational wave emission. Finally, the stars collide in a spectacular explosion known as a kilonova, 1,000 times brighter than a typical supernova. The intense heat and pressure generated during the merger can trigger the formation of heavy elements through a process called rapid neutron capture, or R process. These newly forged elements, along with debris from the shattered neutron stars, are blasted out into space, enriching the surrounding interstellar medium with the building blocks of planets and life. Neutron star mergers are thought to be a major source of the universe's heavy elements, scattering the seeds of future generations of stars and planets across the cosmos. Section 8. The continuing mystery of neutron stars. Neutron stars remain enigmatic, their extreme properties and interiors shrouded in mystery. Fundamental questions persist, pushing our understanding of nuclear physics and gravity. What is the precise composition of neutron star interiors? Do exotic particles exist within their dense cores? How do magnetars generate their strong magnetic fields? These questions drive research into these fascinating objects. New observational facilities provide unprecedented insights into neutron stars. As we've journeyed through the cosmos, exploring the mind-blowing discoveries that have reshaped our understanding of the universe, we've encountered a breathtaking tapestry of celestial objects and phenomena, each more awe-inspiring than the last. From the expanding universe, a testament to the Big Bang's fiery birth, to the faint whispers of the cosmic microwave background, a baby picture of the early cosmos, we've witnessed the universe's grand evolution unfold before our very eyes. We've delved into the enigmatic realm of black holes, those cosmic monsters that warp space and time, capturing the first ever image of a black hole's event horizon, a testament to the power of human ingenuity and collaboration. We've listened to the universe's faintest tremors, the ripples in space-time known as gravitational waves, confirming one of Einstein's most profound predictions and opening a new window on the cosmos. We've embarked on a search for other worlds, planets beyond our solar system, discovering a staggering diversity of exoplanets, some of which may harbor conditions suitable for life. We've peered into the hearts of distant galaxies, uncovering the secrets of neutron stars, those cosmic cinders with unimaginable densities and powerful magnetic fields. And we've grappled with the profound mysteries of dark matter and dark energy, the invisible forces that shape the universe's destiny, driving its expansion and influencing the formation of galaxies and the large-scale structure of the cosmos. These discoveries have expanded our knowledge of the universe and reshaped our understanding of its history and evolution. Our universe is dynamic, born in the Big Bang and shaped by gravity, matter and energy over billions of years. Our Sun is one of billions in the Milky Way, itself one of billions of galaxies. The cosmos scale and grandeur have become tangible, thanks to astronomers and physicists. We've witnessed the universe's infancy and the cosmic microwave background radiation. We've traced the evolution of stars from their birth to their dramatic deaths as supernovae. One of the most profound lessons we've learned from our exploration of the cosmos is the interconnectedness of all things. The atoms that make up our bodies were forged in the hearts of stars and scattered across the cosmos. The laws of physics unify the cosmos in a single, elegant framework. By exploring the universe, we gain a deeper appreciation for our planet, a pale blue dot in space. Among the most profound questions that have driven our exploration of the cosmos is whether we are alone in the universe. The discovery of thousands of exoplanets, some of which may harbor conditions suitable for life, has fueled our imaginations and ignited our determination to search for signs of life beyond Earth. The search for extraterrestrial life, once relegated to the realm of science fiction, has become a legitimate scientific endeavor, with dedicated missions and telescopes searching for biosignatures, telltale signs of life, in the atmospheres of distant planets. The discovery of even the simplest forms of life beyond Earth would be a monumental event, revolutionizing our understanding of life's origins and its place in the universe. It would force us to confront the profound implications of not being alone in the cosmos, to reconsider our place in the grand scheme of things, and to contemplate the possibility of other intelligent civilizations out there, perhaps asking the same questions about the universe that we are. The search for extraterrestrial life is a testament to the human spirit of exploration, our innate curiosity, and our desire to connect with something greater than ourselves. It is a journey that may lead us to answers we never anticipated and to questions we never thought to ask. As we stand on the cusp of new discoveries, with ever more powerful telescopes and spacecraft poised to unlock the universe's secrets, we are reminded that the cosmos is full of unknowns, mysteries that continue to beckon us forward, challenging us to push the boundaries of human knowledge and ingenuity. The nature of dark matter and dark energy, the origin of the universe, the existence of other dimensions, the possibility of life beyond Earth. These are just a few of the many profound questions that continue to inspire astronomers, physicists, and dreamers alike. The pursuit of these answers is a testament to the human spirit of exploration, our innate curiosity, and our desire to understand the universe we inhabit. As we continue to explore the cosmos, we can be certain that we will encounter even more mind-blowing discoveries, findings that will challenge our preconceived notions, expand our understanding of the universe, and inspire future generations to continue the quest for knowledge. The universe is vast and mysterious, full of wonder and awe, and the journey of exploration, driven by our insatiable curiosity and our thirst for knowledge, is one that will continue to captivate and inspire us for generations to come. The discoveries we've made in space, from the expanding universe to gravitational waves, have expanded our knowledge and inspired generations. Our exploration fosters international collaboration and human ingenuity. Space technologies improve our lives on Earth. Most importantly, it ignites our imaginations and inspires us to dream big. We envision a future as a spacefaring civilization. The future of space exploration is bright, filled with promise. Our journey is a testament to human spirit and